Assignment 1V, Rational Functions and Asymptotes. Today's learning objective is to use limit notation to describe what's happening at the asymptote. Take a look at this asymptote here, which is in green. We're going to learn how to write limits describing the graph behavior when we get close to the asymptotes. This is something new to us because usually we use limits to describe the end behavior of a graph. And now we're using limits to describe things that happen in the middle of the graph. But before we do that, I have to introduce you to a new symbol that you've never learned before until today. And this symbol is when we add a little minus sign or a little plus sign to the top of a number. This is not an exponent, and if there's a number here next to it, it becomes an exponent. If we write a little sign of negative positive without putting an exponent, it means something different. Let's start with the positive numbers because they're a little bit easier to understand. So if I write 3 and put a little plus sign on the upper right, that means 3 and a little teeny little bit extra. For instance, 3.000000005, okay? But if I write 3 minus, I'm saying a number that's slightly less than 3, 2.999999997, okay? An easier way of thinking about it is a little plus sign means a little bit to the right of 3, and a little negative sign means a little bit to the left of 3. On the negative sign, you're going to have the same little thing. If I have a plus sign, it means slightly to the right of -6, and if I have a minus sign, it means slightly to the left of -6. Go ahead and study this graphic to make sure you understand where I got these decimals here below. All right, let's move into example 1 in 1.9, vertical asymptotes. So first of all, looking at the graph, it's very clear that I have an asymptote here at -5 and an asymptote here at 2, and therefore I'm just going to write that right there. Now today, we're writing limits about the asymptotes themselves. For instance, you might see a limit as x approaches -5 with a little minus sign, or you might see a limit as x approaches -5 with a plus sign. What's written here in this sentence below explains what that means. X approaching -5 with the minus sign means approach the asymptote from the left. And x approaching -5 plus means approach the asymptote from the right. And to show this, I'm going to zoom in on each part. So what is my function doing as I approach -5 slightly to the left? Well, I go along my function, and as I approach -5 from the left, I'm noticing that my function is ever and ever decreasing to -infinity. The y value goes down to -infinity. It's decreasing without bound. But when I approach -5 from the right side, that's what that little plus means, you're going to notice that my function, as I get closer to the asymptote, is actually going up to +infinity. As the y value goes up to +infinity, it's increasing without bound. Let's do another example. We have a difference of squares in the numerator and a difference of squares in the denominator that's easily factored as such. The goal of the question is to do the limit notation of the vertical asymptotes. Well, looking at this expression, nothing cancels out, therefore there are no holes, and everything in my denominator tells me where the asymptotes are. I'm going to have an asymptote at x equals -2, and I'm going to have an asymptote at x equals 2. I also have the same power in the top and on bottom, which means that I'm going to have a horizontal asymptote of 1. And that's because the ratio of leading coefficients is 1 divided by 1, which equals 1. The top part of my rational function determines where the zeros are at. I know there's going to be a 0 at -3 and a 0 at 3. And what else is also easy to find is the y-intercept. Y-intercept happens when x equals 0. If x equals 0, these two terms will disappear and I will have negative 9 divided by negative 4. And negative 9 divided by negative 4 is 2.25, which is this point right here. And now I know rational functions, kind of how they look. I'm expecting there to be something that hugs these asymptotes down here going through the 0. Over here, I'm going to have something hugging these asymptotes but going through the y-intercept. And then I'm going to have another function going through 3 over here. Of course, you can use the Desmos graphing calculator to figure that out. Now that we've graphed it, we can now approach the question. Find the limit notation of the vertical asymptotes. Well, there are two vertical asymptotes, one at -2 and one at +2. Moreover, each asymptote has two sides, slightly to the left of it and slightly to the right of it. So let's start with slightly to the left of our first asymptote, what I'm going to call section A. My function is obviously going down to -infinity. So as x approaches -2 from the left, my function approaches -infinity. Up here on the right of the asymptote, at a number slightly larger than -2, my function is going up to +infinity. These two limits describe the first asymptote. Now it's time to go to the next asymptote. This asymptote is located at +2, and I'm going to analyze it to slightly to the left. I notice my function is going up to infinity, so when I'm slightly to the left of 2, my function goes up to +infinity. When I'm slightly to the right of the asymptote, my function is approaching -infinity. Tables can also help us do this. Take a look at example 3. We have function g. In the denominator, I have x minus 2. That already rings a bell to me that x can never equal 2. This means I either have a whole or an asymptote at 2. Well, let's look at the numbers close to 2, but not equaling 2. To do this, I'm going to build a table in Desmos. In Desmos, I plug in the rational function that we're analyzing. I notice that I do have a vertical asymptote here at 2, that my graph is doing something different on both sides. And when I put my table in, I replace it with values close to 2, and I get closer and closer to 2, and I'm noticing that my y values are going larger. So let us populate the table with those numbers, and basically I can see that at numbers slightly to the left of 2, my function is approaching -infinity. Now let's change it to numbers to the right of 2. I'm going to get closer and closer to 2 without touching it, because if I put 2 here, it's going to be undefined. But a number that's slightly to the right of 2 gives me a very large positive number. So filling these into our table, I'm noticing that numbers to the right of 2 approach +infinity. So in summary, as x approaches 2 from the left, my function approaches -infinity. And as my x approaches 2 to the right, my function approaches +infinity. Example 4, you're going to try on your own, but I have to give you a little bit of information before you can do that. So take a look at function h, where we have two quadratic functions, one in the numerator, one in the denominator. If I factor out the top part, I'm going to get x plus 6 times x minus 2. What makes this one different is I have a multiplicity of 2 for the bottom factor. That means that x minus 2 cancels out once. Now, normally, this would mean a whole. But in this situation, since I still have an x minus 2 remaining in the denominator, it is still going to be a vertical asymptote. And with that information, you should be able to complete example 4 on your own and check the key to see if you are correct.